The multigrid method is a really effective method of solving large sets of linear algebraic equations that often arise in CFD codes. If you've thought about this topic before, you may have intuitively expected that on a coarser mesh, sets of linear algebraic equations are faster to solve because the matrices are smaller, and so maybe the multigrid method seeks to utilize this feature by solving first on a coarser grid and then using that as an initial condition for the solution on the fine grid that we're actually solving. However, if you look through the literature and the various CFD user manuals, you can see that actually there's a lot more going on here than this simple idea, and often the literature can be quite confusing to understand for the multigrid method. What I've sought out to do in this talk is to actually simplify and actually present the key ideas that are fundamental to the multigrid method so that you can go back to the literature and your CFD user manuals and actually have a good idea of what's really going on behind the scenes. This is going to be a two-part lecture series where I go through first the key ideas behind the multigrid method in this talk, and then the methods that are used to transfer between meshes in the second part of this lecture series. It's well worth you watching both parts of the lecture series all the way through to the end because there's lots and lots of nuanced information that's actually missed out in a lot of the explanations you'll find in the user manuals and in the references. So well worth watching all the way through to the end. All right, if you're excited for this talk, let's get into part one of my series on the multigrid method. To explain the multigrid method, I'm going to be using the example problem you can see here on the slide. I'm going to be considering 2D steady-state heat conduction in a square plate with dimensions of 4 meters by 4 meters, as you can see on the slide. This plate is held at fixed temperatures on its sides. We've got 100 degrees C on the left, 150 degrees C on the bottom, 200 degrees C on the right, and 250 on the top. So I'm just using this anti-clockwise orientation for those temperatures. And the plate is going to have a thermal conductivity of 100 watt per meter Kelvin, a volumetric source term of 1000 watts per cubic meter, and a thickness of 0.1 meters. And I'm dividing this geometry into a mesh of 8 by 8 cells, as you can see there on the slide. And using the finite volume method, we can assemble this problem into a matrix equation of the form AX equals B. And I've been through that process in previous talks, and you can also find it in my courses and in the various sources in the literature if you want to know how the matrix equation is assembled. But I'm not going to be focusing on that in this talk. In this talk, I'm just going to be going through the multigrid method and how we can solve the matrix equation. And just as a quick reminder, AX equals B, here because we're considering the energy equation, X is the vector of unknowns, which here represents the temperature at the centroid of each of those cells in our 2D mesh. Now, to solve this matrix equation, we could use the Gauss-Seidel algorithm. And if you want some information on that, I've been through that in a previous video, so you can find details of how that algorithm works there. But for this talk, what I want you to think about is using the Gauss-Seidel algorithm. What we're going to do is just plot the solution as it converges over each of the iterations or sweeps of the Gauss-Seidel algorithm. And if we start from the image on the left, we can see the solution after a single iteration of the algorithm. And what you can see is that the bulk of the temperature of the plate is still at around 200 degrees C, which is the initial condition that I applied here, or the initial guess. And you can see that the effect of the boundaries, recall that we have 100 degrees C on the left, 150 on the bottom, 200 on the right, and 250 on the top. The effect of that boundary has propagated in by about a cell, or maybe slightly more, depending on the shading of the colours. So we can see that the effect of the boundary is starting to propagate inwards from the side, and the centre of the plate is relatively unaffected after one iteration. And as we move to iteration 2 and then through to iteration 5, you can really see through the colour map that the effect of that boundary is propagating inwards, and then after we reach iteration 5, the effect of the boundaries is reaching somewhere near the middle. And if we continue all the way through to 10, 15, 20 iterations, we can see that eventually the solution appears to be relatively unchanging, and we could make an assessment of whether our algorithm has converged. The important thing to note with the Gauss-Seidel algorithm is that it's relatively slow to converge. And what we would like is we'd like a method of accelerating the convergence so that we can arrive at this final converged steady state temperature field in fewer iterations, because ultimately this will mean that our CFD code speeds up and we get our answer faster. So how can we accelerate the convergence of the Gauss-Seidel algorithm as it is? Now, in the previous talk I did on the Gauss-Seidel algorithm, I went through some specific changes you can make to that algorithm to improve its convergence slightly. But what we want is we actually want a significant improvement in the convergence of the algorithm, and that's what the multigrid method is going to give us. So, how do we accelerate convergence? The first thing that we need to know is we need to know how our solution is converging. Because once we know how it's converging, we can come up with a method of accelerating the convergence. And what we're going to do to look at the convergence is we're going to look at the iteration error. And the iteration error is just the difference between the current solution, x being of course the vector of unknowns in our matrix equation, which represents the temperature at the centroid of all of the cells in the mesh, and then x final being the vector of temperatures when the solution has converged. And the iteration error is just the difference between that current solution and the final solution. And what we're interested in here for improving the convergence of the algorithm is we want to know how does that iteration error vary spatially across the mesh, and how does that error change as the solution converges. So why don't we just have a look? Why don't we plot what the iteration error does? For this example problem, I know what the final solution is, so just for illustration here, I've calculated the difference between the current solution of the Gauss-Seidel algorithm and the final solution, which I happen to know, and then plotted that iteration error as the solution converges. And the contours here are shown in blue, where the dark blue indicates where the error is large, or where we're a long way from convergence, and as we get more towards the white end of the colour map, that indicates the error is much smaller and we're closer to convergence. And what I want you to focus on is that after the first two iterations, if you just look at the spatial variation of the iteration error, you can see that between adjacent cells, the error can be significantly different. It may differ by more than an order of magnitude. Some of the cells are white and next to dark blue cells. And what we describe this with is saying that the error varies spatially with a high frequency in space, not in time, in space. The error varies between adjacent cells. And over the first 5 iterations, we see that the error does vary with high spatial frequency. But as we proceed through the iteration of the Gauss-Seidel algorithm, quickly we see that the error field starts to resemble something like a blob of high error in the middle of the mesh, and then low error towards the edges of the mesh. But more importantly, this distribution, as you can see, is fairly smooth. Those high frequency variations in the error between adjacent cells are gone. They've been smoothed out by the solver. And of course, as we move from iteration 10 to iteration 15 to iteration 20, the iteration error reduces across the mesh. So this dark blue gets lighter and lighter. And when our solution converges, of course, we would expect this entire error field to be white. So we can see that the dark blue blob is getting lighter and lighter, but most importantly, the shape of this iteration error field is staying fairly consistent. It's staying the same. We have that same distribution, and we say that the error varies with a low spatial frequency across the domain. And that's going to be really important for us putting together the multigrid method. And what I want you to do now when thinking about the iteration error and the error as a field, I want you to think of it as a combination of these spatial frequencies that we've just been looking at. And the way you can think about that is if you were to plot along a line through the mesh and plot the iteration error, low frequency components would look like low frequency waves, and then high frequency components of the error would have those oscillations that vary between adjacent cells. And of course, if we were to actually do this and plot along a line through the error field, we'd see some combination of both the high and low spatial frequencies. That's how our error field is likely to look. But of course, we can think of that as a combination of low and high frequency components. And actually, that's what I'm going to go ahead and do for this example problem. If we plot along a line straight through the middle of our iteration error field, and we plot that on a graph of the error on the y-axis, and then x being the distance across the mesh on the x-axis, if we start at the top and look at the black line, this is the variation of the normalized iteration error across the mesh. And of course, the value is very high. It's a large error. It's close to 0.1 because we're right at the start of our Gauss-Seidel iteration. And we can see straight away from that first cell to the second cell, we've got these high frequency components of the error are present in the first iteration. And when we move from iteration 1 through to iteration 5, moving down to the red line, the iteration error has of course reduced. We're getting closer to convergence, but those high frequency components that vary between cells are still there. Once we get to iteration 10 and iteration 15, we can see that the variation of the error is indeed smooth. It now looks like a low spatial frequency. And of course, it's lowest at the edges of the domain because that's where the boundary conditions are, and the boundary condition effect is propagating inwards, and that's why we have the peak in the middle and the lower values at the outside. And as we go down to approach convergence, the distribution, the low spatial frequency, is still present, but the number is reducing and we're getting closer and closer towards 0. And that's what I want you to think about, is that what we want, remember, is to accelerate the convergence of our algorithm. And what's going to be slowing down the ultimate convergence of our algorithm is this low frequency component of the error. If we were able to remove this somehow and get towards a flat line, then our error is actually much closer to being 0, or a very small number, throughout the entire mesh. Because ultimately, remember, we need our error to be low everywhere. And so it's this low frequency component that takes a long time for the Gauss-Seidel algorithm to remove. It is reducing over time, but if we could find a way of removing it quickly, then we could get the algorithm to converge in much fewer iterations. And that's the motivation behind the multi-grid idea. What we're going to do is we're going to use a very simple idea to remove those low frequency components of the error. What we notice is that if we take the same geometry, but we move from a very fine mesh to a coarser mesh, and if we plot the error across the mesh, the low frequency components now become high frequency, because if there's an error on one side of the mesh and a different error on the other side of the mesh, once we coarsen the cells and bring them next to each other, the variation between those two positions is now a high spatial frequency. So if we move to a coarser mesh, we're effectively connecting regions of the mesh that are further away. And once our low frequency components of the error become higher frequency, we can then use the Gauss-Seidel algorithm that we saw before and remove those high frequencies, because the Gauss-Seidel algorithm is very effective at rapidly reducing the high frequency components of the error. And ultimately, that's because the Gauss-Seidel algorithm uses a weighted average of the neighbor cells that surround each cell. And if you want to understand that in a bit more detail, go back and watch my previous video on the Gauss-Seidel algorithm. So this is the first idea in the multi-grid method. If we move to a coarser mesh, those low frequency components that limit the convergence of the algorithm become high frequency, and we can effectively remove those in a very few iterations. Now, the next important part of the multi-grid method, this is the second key component, is to do with the method that we use to move between those meshes. Now, if we think about this image on the left, where we have a smooth variation of our error field, if we were to move to a coarser mesh and use interpolation to calculate what the variation of the error is on the coarser mesh, we would of course take the values between these points at the values we needed for our coarser mesh, and you can see that with this interpolation, the error field is well represented with interpolation because it is a low frequency or smooth field that we're interpolating. However, if our field had high frequency components, you can even think of this now, if you are to draw a line up to this high frequency field at the position of the coarser centroids that you need and take those values and then interpolate between them, you can see that this new interpolated field, the blue line, is actually a really poor representation of the previous field. And so we've actually got a large interpolation error there. So moving from a finer mesh to a coarser mesh, regardless of what the field is that we're interpolating, we need the field to be smooth for us to have effective interpolation. If we don't, we have large interpolation errors, and this could slow down the convergence of our algorithm. And officially this effect is called aliasing, where if we sample at a low frequency from a high frequency variation, we get large interpolation errors. So this is the second idea of our multigrid method. We want to move from a fine mesh to a coarser mesh so that we can have that error component exposed as a higher frequency so we can remove it. But we also need the error field to be smooth first before we interpolate so that we can avoid these aliasing errors. So how do these two ideas combine together into the multigrid method? Well, if we think back to the variation of our error field in our example problem, what we would do for the multigrid method is start off with a few iterations of the Gauss-Seidel algorithm. In this example, we may decide to do 10 iterations, for example. We do 10 iterations of Gauss-Seidel on the original mesh, and the error field changes to go from the black line, which has high frequency components and low frequency components, to the error field that we get at iteration 10. And at this point, the error field is smooth. The error is still quite high. As you can see, it's somewhere between 10 to the minus 2 and 10 to the minus 3. It's quite high, but it's smooth, and that's the important thing. Then what we do is we stop the iteration of the Gauss-Seidel algorithm. And when we use this approach, the Gauss-Seidel algorithm is called a smoother and not a solver, because all we've done is done a few iterations following the same process as normal, but then stopped when we have a smooth field. If we wanted it to be a solver, we would carry on all the way down until that error was reduced all the way to below the tolerance. So we're going to do a few iterations to smooth the field and then stop. And then once we've done that, we've now got a smooth field that we can interpolate onto a coarser mesh. And of course we won't get those aliasing errors because we're interpolating a smooth field. And then those low frequency components of the error that we have are now high frequency. And so we can carry on with the Gauss-Seidel algorithm, but on a coarser mesh, and effectively remove those low frequency components. Again, this is more smoothing. And then when we've done that, and we've made our low frequency components of the error very small, we can move back to the fine mesh and do a final few iterations all the way down to the end of the Gauss-Seidel algorithm when our error is below the tolerance. And this is the final solving part. So you can think of this as we're taking out the middle part of the Gauss-Seidel algorithm. After we've done those first few smoothing iterations, the middle part where we have to spend a long time pulling the low frequency components of the error down, we're going to do those instead on a coarser mesh where we're much quicker, and then move back to Gauss-Seidel for the final few iterations of the algorithm. Now I want to spend a few minutes talking about the residual, because this is another key component of the multigrid method. Now, if we think back to the equation that we've used for the iteration error in equation 4, the iteration error is the difference between the current solution and the final solution. Now, the problem with this is, of course, in a real CFD simulation, we don't actually know what the final solution is until we've solved the problem. I only used it here for the example to demonstrate how the iteration error varies throughout the solution. So what this means is that in practice, we can't use the iteration error to assess convergence. We need to use something else. And the quantity that we use, many of you will be aware of it, is the residual. And the residual is defined using equation 5. So what do we do? How do we use the residual to evaluate convergence for real CFD codes? Well, what we do is we calculate a single iteration using the Gauss-Seidel algorithm. That gives us our current solution vector x. Then we substitute that into equation 6. We know the b vector, we know the A matrix. We evaluate this using matrix multiplication and subtraction, and that gives us the residual vector. And we do this calculation every iteration. So we calculate an iteration of the Gauss-Seidel algorithm. evaluate the residual, and when the residual is sufficiently close to 0, that tells us that our equation is converged. Why does it do this? Of course, when the residual r is equal to 0, that means b minus ax is equal to 0, or ax must be equal to b. So r is another method that we can use to indirectly assess convergence. So how does the residual vary if we plot it spatially throughout the simulation? Well, it turns out that the residual actually converges in a very similar manner to the iteration error. And I've plotted this again as a spatial field. And if we look at iteration 1, so we've done one iteration of the Gauss-Seidel algorithm. We've taken that current solution x and calculated b minus ax to get the residual in every cell in the mesh and plotted it. And once again, you can see that we've got the high spatial frequencies. The residual can vary considerably between adjacent cells. And over the first 5 iterations, we can see this, that those high spatial frequencies are also present in the residual. But when we get more towards 10, 15, and 20 iterations, once again, we see that the residual field is spatially smooth. Those high frequency components have disappeared, and we've got this blob of high residual near the middle of the mesh. And as the simulation converges, the residuals all reduce, but the distribution and the shape of this residual field stays the same. And so we can say that both the iteration error and the residual fields are smooth after, say, 5 to 10 iterations of the Gauss-Seidel algorithm. So I just wanted to make a small side point here that, of course, for CFD simulations that you're used to carrying out, what the CFD code does to represent convergence is we have a residual at the centroid of every cell in the mesh. The CFD code will take the norm of this residual field to produce a single value. And this is the value that you'll often see on the residual plots. It's a representative value that's representative of the residual in every cell in the mesh. And I've just given an example here of the 2 norm. You can see how what you would do is take the magnitude of the residual in all of the cells in the mesh, square it, sum them together, divide by the number of cells and take the square root, and that would give you a representative scalar value that you could plot. So that was just a small side point. That's how residuals are normally tracked in CFD, but for multigrid, we're interested in the spatial distribution of the residual, and that's what we're talking about here. So just a reminder, how does the standard Gauss-Seidel algorithm work? Well, what we do is perform a single iteration on ax equals b to calculate the solution vector x, and then we substitute that into the residual equation. We evaluate b minus ax to get the residual field, so the residual at the centroid of all of the cells in the mesh, and then we use some scalar norm of this value to give us a single number that's representative of the residual in all the cells in the mesh. And if the residual is less than the tolerance, then we have convergence. But if it's greater than the tolerance, we go back to step 1, perform another iteration of Gauss-Seidel, and continue through with this loop until our residual is less than the tolerance specified. But how do we extend this into the multigrid method? We've seen the ideas previously. We've got a good idea of how we can smooth with Gauss-Seidel and how we might want to interpolate onto a coarser mesh, but how do we actually do this? And at this point, I wanted to make a very, very important point, which is a common misconception in the multigrid method, and that is we can't just take this original equation, ax equals b, and solve that on a coarser mesh. So we couldn't just move to a coarser mesh, solve ax equals b on this new mesh, because the solution field x is not smooth. What I've shown you in the previous contours is that it's the iteration error and the residual that are smoothed by the Gauss-Seidel solver, but not necessarily the solution field. And of course, that's because the solution field may have source terms or other nonlinearities and non-smooth features in it, so we can't just move to the coarser mesh and solve the same equation. We need to do something different because it's the residual and the iteration error that are smooth, and we can transfer those between meshes. And that motivates the idea of the correction equation. This is a really, really important aspect of the multigrid method. So let's think back to our residual equation. Once we have our current solution from the given iteration of the Gauss-Seidel algorithm, we can evaluate the residual r. And what we would like is we'd like the next solution that we have in the next iteration of the algorithm, which I've called x new, to satisfy ax equals b exactly. So that's what we would like to happen in our next iteration. And what we're going to do is combine equation 9 and equation 10 together. And the easy way to do that is to replace b in the residual equation by ax new. That arrives at equation 11, which you can see there. And of course, a is common to x new and to x, so we can bring it outside. So we've got a multiplied by the difference between the new solution vector and the current one is equal to the residual vector. And what we then need to do is define a new field, delta x, which is the difference between the next solution and the current solution. I've called that delta x, and this allows us to arrive at equation 14, which is called the correction equation. And this is also a matrix equation, just like ax equals b. We've got our square matrix A, we've got our source vector on the right hand side, and we've got our unknown solution vector here. You'll notice that the A matrix is the same, but the B vector on the right hand side is now the residual vector, and the solution vector is the correction to the current solution. So what does this mean? Delta x is the correction at the centroid of every cell in the mesh, which would tell us how we can move from our current solution to our next solution. The really important thing about this correction equation is that delta x is actually an approximation of the iteration error. And if you look in equation 15, you can see that delta x, of course, is the difference between x new and x, whereas the iteration error, e, is the difference between the current x and the final solution. So as we approach convergence, so when we've done maybe 10, 15 or 20 iterations, of course, x new is going to tend towards x final. And that tells us that because delta x, the correction, is an approximation of the iteration error multiplied by -1, then that tells us that the correction will be smooth after a few iterations of the Gauss-Seidel algorithm. The iteration error is smooth, so the correction will also be smooth. And that is a really important result that's missed out of many different discussions of the multigrid method. Because the correction is smooth, that means we can transfer it between meshes in the same way that we can with the iteration error and the residual. We can transfer it between meshes without those aliasing errors if we've done a few iterations of the Gauss-Seidel algorithm. So what we're going to be doing is actually solving the correction equation on a coarser mesh, not the original equation. That's the key point of the multigrid method. We're going to solve the correction equation because the residual vector r will be smooth and the correction vector will also be smooth after we've done a few iterations of the Gauss-Seidel algorithm. So I've described this as an alternative algorithm. How do we pull all these features together? Well, what we do is we start out by performing a few iterations of the Gauss-Seidel algorithm on our original equation, on our original mesh, ax equals b, to calculate x. That's our current solution. And as before, as normal, we calculate the residual vector. R is b minus ax. And now this is the key point. The residual vector r now becomes the source term, or the right-hand side of the correction equation. So we now have a source term r, which becomes a source term for the correction equation, and we're going to solve the correction equation instead of the Gauss-Seidel algorithm on the original matrix equation. So let's say, for example, that we did 10 iterations on ax equals b. We did 10 iterations, we calculate the residual vector r, and then we do the remaining 20 or 30 iterations on the correction equation instead. So we haven't actually changed the number of iterations. All we've done is we've gone from solving ax equals b, we've stopped after we've got that smooth solution, and we've now moved to the correction equation, a delta x is r. And of course, once we've solved the correction equation for delta x, we've got our final solution, we can then just add that to the solution x, and that gives us x new. So we've arrived at the same place, we've calculated x new, but instead of just doing 50 or 60 iterations with Gauss-Seidel, we've done 10 iterations, we've stopped, and then we've moved to the correction equation, solved that instead, and then corrected the solution vector x. A really important point of this is even though we've got a new algorithm, this algorithm is not actually any faster than the standard Gauss-Seidel algorithm because we've just swapped from one matrix equation to another. We haven't got any input performance improvements at this point. But the key point is that we can transfer the correction equation to a coarser mesh as R and delta X are going to be smooth once we've done 10 or so iterations of the Gauss-Seidel algorithm. And it's this process of moving the correction equation to the coarser mesh that actually gives us the acceleration in the multigrid method. And that process of moving between meshes, I'm going to do in detail in the second part of this lecture, and that's going to be coming after this video. So just a quick summary of what we've talked about today. The Gauss-Seidel algorithm is really effective at removing the high spatial frequencies in the error field in the first few iterations. And this is described as smoothing the error field, or is why Gauss-Seidel is often called a smoother and not a solver in the context of the multigrid method. It is otherwise identical. And what we want to do in the multigrid method is move to a coarser mesh, because that means that the low frequency components of the error field are now high frequency and they can be easily removed by the Gauss-Seidel algorithm. And of course, because we have a coarser mesh, those iterations are going to be faster to perform. And a key point of this moving between meshes is that the field that's being moved between meshes needs to be smooth to reduce interpolation errors. And this is formally called aliasing. And it's the residual vector and the solution update that are smoothed by Gauss-Seidel, not the solution itself, and that's why those quantities can be easily transferred between meshes in the multigrid method. So that brings me to the end of part 1 of my lecture series on the multigrid method. Let me know in the comment section, did you find this talk useful? I'm really hoping that after watching this lecture series, you'll be able to go back to your various references and resources on the multigrid method and user manuals for your CFD codes, and to understand actually what the code is doing and why as it moves through the multigrid method. If you did find this talk particularly useful, feel free to share it with a colleague or a friend. Point them in the right direction. I'm really hoping that this can help everyone improve their understanding of the multigrid method. Till next time, thank you all very much for supporting the channel and watching my videos. I do really appreciate it. And I'll see you in part 2, where I go through the methods that we use to move between meshes in the multigrid method.